bright, so we'll be in probably some dinner, but thanks for coming anyway. Where to start? For years, I've been wondering, where is Trinidad going to be going next? What can I be doing next towards Trinidad's oil and gas exploration? And it became increasingly obvious that exploration was moving into deep water. So I pondered, what could I do? And I found out, just by browsing online, I found out that I was eligible to receive samples from a thing called the deep sea drilling program. It later became what's called the Ocean Drilling Program, the ODP. All I had to do was fill out a form which required me to put forward a hypothesis, which I'm okay at generating hypotheses. I'm not very good at showing whether they're right or not. But I send them the hypothesis, and they say, okay, we'll send you some samples you can test it. You can use to test that. And so over the years, I've built up an expertise in deep and ultra-deep water rocks, things from backfield, lower backfield to abyssal environments. I got in touch with a colleague at the Smithsonian, a statistician called EMILIANI. Her name's going to come up. And she very kindly said to me, I've got this little index, why don't you try it on your data? It's never been published, I don't know what's going to happen, but here's the formula. She sent it to me, it didn't even have a name at that time. It was just a formula. I said, I'm going to call this the Assemblage Turnover Index. And we applied it to some of my deep water data, and we discovered that in fact this thing, which could be done by anybody with high school maths, it has potential for correlating deep water successions. It even has potential, and this is what really excites me, it even has potential as a sequence stratigraphic tool for deep water successions. For years we've been told that there are successions bounded by sequence boundaries on the shelf, and then there's this vague mention of correlative conformities in deep water that we have real trouble finding. But I'm going to show you that we can use this as a sequence stratigraphic tool. But it doesn't show us sequence boundaries, nor does it show us maximum fluid surfaces. I think everyone knows the chance of that. It shows us the transgressive systems trap. Okay, this lecture, it says there, I'm giving it as part of an agreement with the Ministry of Energy. They've given me some money to take this forwards. And so I said, in that case, I'll give some talks where I announce to industry my results so that they can get excited and bring me more work. I hope that's going to happen. We've got students present. I see they've segregated themselves by years. Third year, second year, first year. Not all of whom have yet got the experience that some of us do. So there is going to have to be some background to this before I get to the turnover indexes. So I hope the rest of you find it entertaining anyway, because I've got a slightly different take on sequence stratigraphy that I'm going to present to you. I'm going to start with I'm going to start with what I call an advanced organizer, which is a tool from education. Those of you who are going to be doing presentations, you will take note. Give your conclusions first. An advanced organizer. So that as the audience goes through, they can tick off, yeah, I've seen that, seen that, seen that, instead of having to remember loads of stuff and then you get to the end of it thinking, maybe I saw that, maybe I didn't. So what am I going to show? I hope those of you at the back have got really good eyesight. This is the one slide that's got lots of words on it. I don't normally like to read slides to you, but in this case I will anyway, because the conclusions are important. So, climate in the Pleistocene changed between icy glacials and warmer interglacials. Times when a lot of our planet was covered with ice, and other times when the ice had disappeared. This was, for the last million years or so at least, this was driven very much by changes in the shape of the Earth's orbit around the Sun. I'm going to demonstrate this to you. This is in turn reflected in the rock record, because any creatures that secrete shells made from calcium carbonate, well, the oxygen isotope ratio in that calcium carbonate reflects the ice volume. The onset of glacials is very slow, and there's a very rapid melting, which is why transgressive systems tracks in sequence stratigraphy tend to be so thin. And then I'm going to show that this is reflected in deep sea foraminiferal assemblages, benthic assemblages. I know there are plankton foraminifera, things that float around in the seawater. Frankly, they've never excited me. I've tried. They look like popcorn. I'm sorry, this is going to get into trouble when we put this online, isn't it? But I'm going to work with benthic ones only. I'm going to show that there are no distinct glacial and interglacial foram assemblages, which is something people have been searching for decades. How can we recognize a glacial versus an interglacial on the fauna? The truth is we can't. What we can do is use the ATI, the Assemblage Turnover Index, to show when we go from a glacial into an interglacial. I'm going to show how we can use this to correlate. So my starting point is these two fundamental. I hope you remember, I filched that from the internet. I did not do that myself. I wish I could boast. I found it and copied it. I didn't even realize it moved at the time. But there we go. With two interacting and quite different factors I'm going to put together. So the Earth's orbit changes through time. There's a picture of our planet taken from the moon by NASA, showing a nice blue planet there, lots of clouds and continents and stuff. And then we've got 3 stable isotopes of oxygen in the stuff that makes the Earth blue, in the water that makes the Earth blue. So I'm going to put those two ideas together and produce something that hopefully goes beyond those simple ideas. So let's start with Kepler. Kepler was an astronomer in the late 1500s, early 1600s. Got hold of one of those newfangled inventions called a telescope. Telescopes to us, they're nothing nowadays. You can buy one at, I'll say, if you wish, in the $10 store. But back then, producing lenses was a major thing, and telescopes were certainly a very expensive novelty. Kepler got hold of one of these. Most people are looking at planets and stars. He had the good sense not to look through his telescope at the sun, because that would destroy his eyesight. But what he did was he took a sheet of paper, put it behind his telescope, and found that he could reflect a picture of the sun onto it. He could reflect, isn't quite the word, project a picture of the sun. We knew at that time they'd already worked out that the Earth's axis is vertical, that it's got a tilt. And he measured the diameter of that reflection repeatedly throughout the year, over several years. And he found that it got larger and smaller. Some of that could be explained because the Earth's axis was tilted, but not all of it. And to explain that, he came up with the idea that the Earth's orbit around the sun is not a circle, like I was taught in primary school. We go round the sun, that sounds like we go round in a circle. No, he said we go round in an ellipse. An ellipse which has 2 foci. One of those is the sun, and the other one is nothing there. So his first law was that planets move in ellipses around the sun. His second law was that if you draw a line from our planet to the sun, and you measure the area which that traverses in one, the area is a constant. In other words, when we're near the sun, we move a lot faster than we do when we're further away from it. When we have a very elliptical orbit, our planet spends most of its time farther away from the sun. So what Kepler didn't know, he was able to work this out using his telescope and a sheet of paper. But, well, let's go on to another chappie, POINCARE. In 1899, the King of Belgium, I think it was King Leopold IV, realized that his birthday was coming. One of those important birthdays. You know, because we work with decimals, we all think 50 is more important than 51. Yeah, except when you get to 51, and you go, whoa, I'm 51. Yeah, but he got one of those 0 birthdays coming up. And he said, for my birthday present, which is going to be 1903, I want somebody in Belgium, I'm going to have a competition, I want you to come up with something that will wow the world and say Belgium is a country to be reckoned with. And POINCARE bought into this. There was a prize, I don't know what the prize was, I don't know, chocolate eggs, something like that. But he bought into that and he said, okay, I'm going to ask the question, is our solar system in a steady state? In other words, are we going around in this ellipse, but the ellipse never changes? And his thinking was that we have the sun, which has its own gravitational attraction, but we have other planets, some of which are extremely large, Jupiter, Saturn, and so on. He said, what does their gravitational field do to the effect, how does that affect the Earth's orbit? If we were in a steady state, we'd go around in the same ellipse all the time. If not, then the shape of that orbit would change. It was a massive problem. He didn't have computers at that time. He didn't even have fucking calculators, and he had to solve 18 equations, differential equations, in order to come up with his model. But what he said was, I'm going to take just the Sun, the Earth, and Jupiter, and I'm going to model what would happen to the Earth's orbit. And he found that it fluctuates between being nearly circular, slightly elliptical, but nearly circular, to being much more pronounced elliptical. He also found that with this, what he called the three-body problem, he found that it was a chaotic system. In other words, there's no regular going from circular to elliptical and back again. Because the Earth's position relative to Jupiter is constantly changing. At the same time each year, they'd be in different positions. So that was the first mention, really, of chaos theory. I don't know if anybody knows chaos theory. It's wonderful stuff. Where it says subtle differences in the starting situation for anything can lead to pronouncedly different results. So this is a nice picture that I borrowed from. It's a book by William Hayes. He's a micropaleontologist, works on calcareous nanoplankton. He's published a book called Experimenting on a Small Planet. Please buy a copy. I'm sure you'll appreciate royalty. It's quite cheap. It's only about 30 euros. This is a picture that I stole from it. A nice cartoon that says, when we've got an orbit which is nearly circular, then we have a nice equable climate. But when we have an elliptical orbit, there's going to be a period where we're very hot, but for most of the time we're going to be further from the sun, and really cold. And remember, we move faster when we're nearer the sun than when we're farther away. So during that cold period, we will get ice developed. If there is not sufficient of a warm summer to melt all that ice, we will get an ice buildup. A gentleman in the 1870s, around the Agassiz, has already come up with the idea of an ice age. He's seen features in Switzerland that to him suggested that the planet had been coated in ice at some time. And this really brought into that idea. He provided a nice confirmation there. There are other confounding factors. I'm not going to pretend that the shape of the orbit is the only thing that controls whether we have a glacial or an interglacial climate. There is, for example, the slope of the Earth's axis, and how it slopes relative to the sun. Our planet at the moment, it wobbles. We can't feel it, we don't get seasick, because it wobbles on a very slow scale, about every 41,000 years. So it's a bit like if you've ever played with a spinning top. When it gets towards the end, it goes on wobbly. But we're in that sort of state. So, if the Earth's axis, if we're wobbling so that the Earth's axis, while we're away from the sun, is pointing away from the sun, things will be super cold. If it's pointing towards the sun, then it's not going to be quite as drastic. And I've tried to show that there with a blue axis for cold and a red axis for when things will be warm. But if we look over the last million years or so, that shape of the orbit has been the major control. We have at the moment what we call a 100K cycle. If we go back before 1 million years, then the tilt was more important. We had a 41K cycle. So, we have a Pleistocene ice age, where ice formation is driven by the shape of the orbit. We get a buildup of ice, a huge buildup of ice. There's a map there of how things were about 25,000 years ago. Most of North America was covered with ice. If you went to Chicago, there'd be a layer of ice. We've modeled it. It's about 3 kilometers thick. If you go to Central Park in New York, you can see glacial features, what are called sheep-shaped rocks, rock moutonne, in Central Park, that formed within the last few 100,000 years. So we have glacials, interglacials. By the way, while we're looking at this, with a pointer that does not work, and why don't I just walk up to it instead and point? The old-fashioned way. Originally, God made that pointer. I will use it. There's an ice-free corridor there. It's pointing at it. Some people just don't understand technology, you know. I put it down to my age. There's a nice, while we're talking about this map, there's a nice free corridor there. I don't really understand why that. Please go and investigate this for me. Got the whole of North America covered by this enormous ice sheet. Then we've got the Rocky Mountains, the Cordillera covered by an ice sheet. Got this ice-free corridor in between. Don't understand it, but it's on the map. Anyway, so what? You might say, so what? Well, if the continent's covered in ice, that ice has to have come from somewhere. And the truth is, the water came out of the oceans. So sea level varies as we go from glacials to interglacials. If we look on the continental shelf, it's quite easy to recognize. In fact, when sea level is low at the shelf edge, out there, we get sediment which trundles down the continental slope, which gives us a deep sea fan. Second years take note, a deep sea fan. And then as sea level begins to rise, we get what we call the low stand systems tract. But what I really want to draw your attention to is this one, the transgressive systems tract. That occurs between the surface of maximum regression and the time of maximum sea level, what we call the maximum flooding surface. So the maximum flooding surface is the nice blue line, like a sock. Those of you in the second year, you've got lots of work on this to look forward to next semester. Wonderful stuff. But my question was, you know, we're moving into deep water, our exploration is moving into deep water. How can we correlate? How can we correlate when we're not in an area where a deep sea fan is likely to form? Off South America as well, we've got the world's largest river, the Amazon, which is producing an enormous deep sea fan. We've got the Orinoco, the world's 4th largest river. Once again, a huge deep sea fan. But in between them, there's an area with very little deposition taking place. What happens if we go looking in that area? Can we recognize any sequence stratigraphic signal based on foraminiferal temperatures? So let's introduce the oxygen isotopes. Oxygen has 3 isotopes which are stable. We have oxygen-16, which is the main one. Nearly 99.8% of all oxygen is made of that. We have oxygen-18, which makes up about 1/5 of a percent. And then we have a minor part, which is made up of oxygen-17. Oxygen-16 and 18 are the ones that people work with mostly, because the mass spectrometer is able to measure the amount of oxygen-18 in a particular deposit, in a particular calcite crystal. There's a gentleman called EMILIANI did some work on oxygen isotopes and how they reflect in forms. His thinking was quite simple, and I've explained this even to my first year. If you take a bowl of water, or the jug of water that's on the table, it's got a certain oxygen isotope ratio, oxygen 16, oxygen 18, in a certain amount. But in this climate, it's going to start evaporating. The oxygen 16 is the oxygen molecules of water made from oxygen 16 are more likely to evaporate simply because they're lighter. They're easy to evaporate. So as the water level goes down, then we will find there is more and more oxygen 18 within our water. If we can measure that, EMILIANI said, then that will give us an indication of paleo temperatures. He took our familiar, we call it lambi here, don't we? I call it queen con. The Divisions call it queen con. But he took 3 specimens of those and he grew them at various temperatures. How he got it to grow at 7 Celsius, I don't know. I can scarcely function at 7 Celsius anymore. But he managed to. And he found that there was a change in the oxygen 18 ratio. So his thinking was that, once again, he thought we can use this to measure paleo temperature. If we were to take a series of shallow water pokes, planktonic forams, and look at the oxygen isotope ratio, we'd be able to graph that by taking samples through a column and graph that and tell when we were in glacials, when we were deep interglacials. So, this is just sort of encapsulating the idea. Sea level is high in this one, no ice, so we get lots of oxygen 16, 18 here. When we get ice, well, the ice is made up of the lighter isotope, oxygen 16, so the water from which the things we make their shells contain more oxygen 18. Easy. What EMILIANI didn't know, no fault of his, what he didn't know was that if you look at the oxygen isotope ratios in something that lives in the deep sea, this is a UV Urania, and compare it with something that lives in the top few tens of meters of the water column, this is a Globituronoides ruber. If you look at the oxygen isotopes in those, there's really not any difference. We know that the deep sea is colder. It's about maybe 4 or 5 Celsius at the bottom of the oceans. And in the tropics at least, it gets up to a nice equable nearly 30 Celsius, and then gives us hurricanes. That's the whole of the story. But what Shackleton found out was that there was really not much difference in the isotope ratio between these two. A little bit you can describe temperature. Instead, because they were so similar, he said that oxygen isotopes are a measure of ice volume, not a measure of temperature. So this is just some graphs showing oxygen isotope ratios over the last 600,000 years. Various sites there, I cannot even remember where they are. Site 1089, 983, I have no idea where they are. But you can see that we have the same basic signal between each of those. Where the graph is at a peak, odd numbered, those are interglacials. We are living at the moment in what we call green isotope stage 1. The previous interglacial is isotope stage 3. It's a bit of a muted affair, that one. And then we have stage 5, 7, and so on. So if it's even numbered, then it's a glacial. So we can use that as a correlation signal. If we look at the curve, expand it a little bit more, we find that there are these very slow development of glacials, followed by a very rapid melting, a very sudden transgression. Indeed, if we were to project onto that what we would expect from sequence stratigraphy, we can find out where sequence boundaries will be developing, ESBs along the bottom, maximum flooding surfaces, and then the transgressive systems. I would love to say that it's a perfect 100,000 year cycle, but you can tell just looking at that it isn't. The world is a very noisy place. It never quite behaves the way we want it to. So there is a sort of ragged interval there in marine isotope stage 8. I particularly want to draw that to your attention, just because that presents just a slight confounding factor to the model I'm going to present to you. So that brings me to the bugs. Finally, the bit that I enjoy, the 4 amps. First years, you've only seen photographs. You've seen this one already. I boast about it every time. You all know who it's named after and all that. But let's just recap. For those who've gone into industry and forgotten all this stuff, let's just recap what 4 amps are. They're single-celled bugs. I call them bugs affectionately. If I call it a bug, it's because I love it, love it, love it. I live and breathe benthic 4 amps, and I think they're amazing things. Should be taught from primary school onwards. Anyway, they're single-celled bugs, mostly. What can I say? You missed out. I'll make sure future generations get them from primary school onwards. So they're single-celled bugs. They're minute, mostly less than 1 millimeter, and some of them are far less than that. Some of them planktonic. They float near the sea surface. I've already said I prefer to leave those to other people. Some of them are benthic, they live on the seafloor or burrow into it, and those are the ones that I'm interested in. So the rest of my talk is really about the benthic ones. They're shelled, which means that they have a fossil record, which is what makes them useful. I know they're distantly related to the amoeba, and the amoeba doesn't fossilize. It's the fact that we have a shell that means the cows can fossilize, and they're useful to us. They've got narrow ecological niches, which means that if I find a certain species, I've got a good chance of being able to tell how the environment was. I think there's been an over-reliance on that in people trying to put forward stratigraphic models. But they are very abundant in marine environments. Sally and I have both worked on reefal 4 amps. Sally worked around Tobago, I worked around Nevis. If you go to the beach on Tobago and on Nevis and pick up a handful of sediment, there will be several hundred 4 amps in it. Some places in the Pacific, up to 90% of the beach sand is made of 4 amp shells. And I always have to make this comment, they are absolutely gorgeous. They must be because it says so right there. They live in communities. So here's a collection of shallow water 4 amps. These are from around Nevis. I won't bother with any names, but they live in communities. So if I take a sample, I will find lots of different species. Around Nevis, the fauna is dominated by that one, a thing called Discorbis rosea. But communities change over time. There may be a very slow change. The first year we were talking about evolution this morning. Well, there may be a slow change if we look from the bottom of very thick sequence to the top. We'll find different possible because of evolution. But they can also be driven to change, communities change rapidly because of environmental conditions, changes in environmental conditions. So our index was a way of measuring how things change between one sample and the next. If we've taken 2 samples, say, from a core, and we look at the community in one and the community in the next, can we quantify the turnover between them? The formula is really, really simple. If we've got one sample, and we pick out, say, 300 bugs, we can work out the proportional abundance of each species in that sample. Some, the dominant ones, will make up a very big percentage. As we go through, we'll find that they get a smaller and smaller percentage. If we take a next sample, just above it, we'll probably find that there is a different proportional abundance in that sample. If we were to subtract those, and it doesn't matter whether you subtract the top sample or the bottom sample, if you were to subtract those and then add them all together for every species, you'd obviously get 0. As one thing becomes more abundant, some things got to give way proportionally. But if we take the absolute values instead and sum those, we get a non-zero number, unless the assemblages are absolutely identical. And the higher that number is, the greater the change there has been in the makeup of that assembly. I said, okay, let's take a load of samples from some DSTP or GP holes, and we look at what happens to the assemblage turnover index over time. We simply graph it. I said, if we find a peak, 2 peaks in the value of ATI, I'm going to call the interval between it a patty. I don't peak bounded assemblage turnover interval, if you want its full name. But I like it because it sounds a bit like, you know, McDonald's piling up beef burgers, doesn't it? So I've got that image in my head. So, patties. So peaks between peaks I define as being where the value of ATI exceeds the mean plus 1 standard deviation. It's a very crude way of doing it. This really needs refining. But I knew that if I took the mean plus 1 standard deviation, something like 30% of values would exceed that, and that would hopefully give me something I can correlate. We developed another index from it, the conditional boundary index, COBE, where we can work out the proportional contribution of each species to ATI simply by taking that and dividing it by ATI. Easy. Well, I'm not going to. I'm going to concentrate on the assemblage turnover index here. So let me give you an example. Put it into practice. This is ODP site 994C, which is off South Carolina. It's on a place called Lake Plateau. Water depth is nearly 3,000 meters. So even if you've got ice building up and melting, the change in sea level alone is really not going to influence the flows. They're down nearly 3 kilometers. 100 meters water level change from there is not going to go long to them. The sediments, well, that's Lake Quaternary. Lake is part of the Pleistocene plus the Holocene. Marine isotope stage is 12 till 1. And there's a depositional rate of about 3.5 centimeters per 1,000 years. This is my graph of ATI. Please ignore these two. Those should be another talk in themselves, but this is from a paper that we published. This is my graph of ATI. You can see there I have my line of mean plus 1 standard deviation, which means I can indicate peaks. The peaks are in green. What really excited me was when I graphed those back against the oxygen isotope curve for that same succession, I find that the vast majority of these coincide with terminations. They coincide with the transgression. They coincide with the transgressive systems trend. That means we potentially have a way that we can correlate sequence stratigraphically in very deep water, something we've never had before. I would draw your attention to this bit. Remember, marine isotope stage is raggy. Well, there are several peaks within isotope stage 8, which means that we cannot unequivocally say every peak is a termination, but the vast majority there are. Now, one swallow does not make a summer, as we say in my native Yorkshire, which meant I had to go and look at a separate second succession, just to make sure that I was correct. Let's see, move on. Oh, before I do that, I should just add, this is derived from COBE. These are the main species. You can see that there are no distinct glacial, interglacial forms there. The thing that people have been trying to find for years, it does not exist. So, 994C is taken off Suriname. It's on the Demerara Rise. I know that there's the Amazon belching out water, organic stuff, just a few hundred kilometers to the south of this, but the Amazon water stays very close inshore. There's no indication that Amazon water and sediment is confounding things this far from the coast. This succession was a little bit more complex in that it contained two bugs in great abundance, Cassidiolina and Uvigerina. This is graphs of what's called an oxygen minimum zone of California. And we can see that Cassidiolina, this one, lives in shallower water than Uvigerina, this one. This, I thought, might mess things up for me. But when I graphed them, I found that there was a change in the abundance of Cassidiolina, that's this one, which decreased, Uvigerina, this one, which increased. There was a migration of the oxygen minimum zone. But despite that, I found a very good signal of patties and their patty boundaries. What really excited me, by the way, I have no oxygen isotope curve for this well. I should point that out. I would love to have one. I don't have the money. Please go back to your bosses, say this I need money, buy me a mass spectrometer, whatever it takes. But I placed my 994C with its oxygen isotope curve next to 1261A. There we are. And I had a couple of biostratigraphic tie points there, especially the extinction of this thing, EMILIANI and Huxleyi. I found that there was a very, very good correlation between the two. I could correlate those patties between Florida and Guyana. We're in the middle. We should be able to use this for correlating our deep water succession. Is it universally applicable? Well, there was a gentleman called Ryuji, a Japanese gentleman, did some work off the Ryukyu Islands, which is sort of around Japan. He came up with this graph. This is his oxygen isotopes with termination 1, termination 2. He presented his data the way a lot of paleontologists did for decades, simply as a cumulative frequency graph. But if we look, once we're accustomed to looking for the boundaries instead of trying to find the glacials into glacials, we can find T1 just absolutely leaps out at us there. T2, well, that's a bit more muted. There we are. And there are some events happening in between. But this, once again, shows potential for at least regional correlation, if not interoceanic. By the way, he said that this bug, Bulli minor aculeata, he said that he thought characterizes glacials. No, it doesn't. Just look at your own graph. There we are in a glacial. There we are in an interglacial. It's common in problem. And then here, as we're just beginning to enter the glacial, and then at the height of the glacial. It's almost random in its fluctuations. So once again, we're better off using the changes in total ascent rather than trying to use a single bug to try and identify glacials and interglacials. So I ran ATI on it. T1 stands out very nicely. T2, well, it's in there, but there are some other surfaces as well. So I would say that in the absence of an oxygen isotope curve, I would not be confident correlating over such a huge distance as here to Japan. Why it doesn't, why we have these extra ones around Japan, I'm not sure. It's apparently not due to turbidites, even though Japan is a tectonically active area. It could possibly, because of changes in seawater chemistry, the ash from the volcanoes could be changing seawater chemistry. Or it could just be through some small variation in current patterns. I don't know. This is something we need to look into. We've only done this for 3 holes so far. So, this is where we are at the moment. Well, I'm going to move on and do some future work. One thing always leads to another. BG have very nicely given me 5 cores, piston cores, they're about 3 meters long, taken off eastern Trinidad. They range in depth from about 250 meters there down to 700, a lot shallower than I've worked with so far. I want to know what happens with ATI when we get into shallow water. Do we find there's a drift towards peaking out maximum flooding surfaces? Or does ATI continue to tell us that it's the transgressive systems tract where real change is driven? So that's one thing I'm going to be working on. Then I've got a stack of other projects lined up, some of which I'm getting help with. We're going to have to work out confidence limits on ATI. Well, I'm leaving that to Leanne. She's a mathematician. I just plug things into the computer. What happens when we're before glacial times, before the Pleistocene, before the Oligocene, when we're in a greenhouse type world? Well, the Ministry of Energy has given me money to look at that. The ODP have given me samples to look at that. And I'm able to employ somebody for the first time to work on these samples with me. You've probably seen her show me hanging around with Harvard, but she's now working with me. So her name is there, the Show Me Belfast. What happens to planktonic communities? Lai Shan, I really hope Lai Shan will be here. She's working on that, taking exactly the same successions as I've worked, but looking at the planktonic forams. In industry, we tend to pick the first 200 forams, whether they're planktonic or benthonic, which really compromises the signals we can get. I think by looking at the two separately, we'll find that we get a far better idea of what is going on. Let's see. How does ATI vary within any one formation? Well, Janelle's working on that at the moment. Yeah, she perhaps didn't realise quite yet where her work fitted in. But we've got three sections through the Supero. We'll look at the ATI between those and see how it changed over that one formation. Sadie, in third year, has already sidled up to me and said, can I do a PhD with you, please? So I've said, certainly. Well, I would like to know for Trinidad, I would like to know what happened with the arrival of the Orinoco. Not the Orinoco, the Amazon. What happened with the arrival of the Amazon? Prior to the middle Miocene, the Amazon really wasn't a very important river. Once the Andes have been built, the Amazon built all the way across South America and became the world's largest river. How is that reflected in sediments in Trinidad? Can we pick it up using ATI? This will make use of samples that we took along the new San Fernando Debe Highway. It'll also make use of more material from the Demerara Rise. And then looking at ATI and rapid climate change. Sorry, Adele, your eyes are glazing over. I'm nearly finished. Okay? Oops. Am I going to be in trouble after? Look, if we're heading into uncharted waters at the moment, in the we're all oil geologists in this room, and we think the more oil we produce, the better we are, because we get more money. But we know it's changing the composition of the atmosphere. We know global warming is taking place. People ask, well, what's happened in the past? What happened during the Pleistocene? Well, there's no comparison with the Pleistocene at all. If we want anything comparable, we've got to go back to the Paleocene, Eocene boundary, where there was a very, very sudden release of either methane that oxidized to carbon dioxide, or carbon dioxide itself, within a matter of a few thousand years, which changed the composition of the atmosphere. It produced what we call the thermal maximum, when global temperatures on average went up something like 8 or 9 Celsius. Global temperatures at the poles went up enormously by about 15 Celsius. If we look at that, I think we'll get a far better view of what is going to happen with our current global warming. So that's been worked on by myself, Leanne at the Smithsonian, and we're borrowing data, we're filching data, put it however you want, from Ellen Thomas. So lots of future work coming from this, but here's my conclusions. You've seen them already. We've seen that the shape of the Earth's orbit changes, that produced glacials into glacials, that the sudden transgressions change physical, chemical characteristics of the oceans enough that it drove changes in the fauna. So we can pick out the transgressive systems tracts at some point within it using the Assemblage Turnover Index. Some references, a few by me. Some acknowledgements, well, acknowledgements for Leanne, first of all. because she was the one who developed the index. She handed it to me and said, you play with it, see what you can get from it. And this is what rose from it. She really needs a lot of the credit. Ocean Drilling Program for giving me the samples, thank you very much. Andrew Jupiter at UI for going to the Ministry of Energy and begging for some money for me to take this further. So the Ministry itself for giving me some finance. So, thank you. I'm sorry, Adele. I really am sorry.
Any questions from the floor?
Really clear. Yeah, thank you.
So, Ron Daniel, when do you expect the results of the work on the piston course?
I'm glad you asked. I'm so glad you asked. I've done the first one, and the top core here is one that was published by Baer et al. In 2014. That was taken out 50 kilometers from where I'm working, and they did produce an oxidized tone curve for it. Let's say that my core is comparable. Depositional rates were extremely high in their core, between 13 and 49 centimeters per 1,000 years, giving a nice expanded signal. Well, this is what I found with ATI. This is the bottom of your deepest core, and this is the top. ATI is at a maximum during that transgressive systems track, once again. My question is, well, first of all, these small ones, what are they? Are they effects like the Little Ice Age, for example? Or the early Holocene thermal maximum? Are we picking up those? Or are those local events? I don't know yet. What I really would like to do is see if these peaks are maintained as we come into the shallow water on shores. I'm working on the second core as we speak. Thank you.
Alright, that's it. Thank you, Brent, for
Thank you.
another great talk. And yeah, and dinner is ready outside. So I suggest we grab dinner, come back in, and then get on with the AGM. Okay? Thanks again.